Welcome back. So in the first video, we have created ourselves a little script that we can execute and which will then produce an image like this, where you don't really see anything because the chances of you by accident discovering a strange attractor are just so slim that it would take you forever. Well, not forever. Remember, we got lucky, but it's just so unlikely. Anyway, what we'll now do is we'll go down here and fix a little bug that I noticed where I misspelled the word converging. So I'm just going to copy paste this. But the real action is not going to happen down here. So we are ruling out cases where our system of equation leads to a convergence to infinity. We are ruling out cases where we are converging to a single point, but now we really got to check for chaotic behavior because these are really the images, the patterns that we would like to see. So what we'll do here is we'll go back to the very hallmark of chaotic behavior, and that is sensitivity to initial conditions. Now, if you remember from the first video, I had this little animation of 2 points which were nearby at the beginning, and then they entered on these different paths which diverged rather quickly. So let's go back here where we simulate our random starting point, and let's add another point in the vicinity of that starting point. So we'll say we have a random alternative point that is nearby, and we're going to call that xe and ye, and we'll just say that this is equal to x and y plus, and now we'll just take we'll take what we had before, so random.uniform. I'm going to add this down here, but now we'll divide that by 1000 to really make sure that we are just off by a very little bit. So this is a change on some decimal place. It's not like completely different. It's really almost the same point. It's almost identical. And now we compute the distance between these 2 points. So distance between the 2 points. And here we can use the good old distance equation, distance formula. So we'll say that we have a distance in the x direction, in the x dimension, and this is xe minus x, xe minus x, and dy, then same thing, ye minus y. Now the distance between these two, and I'm going to call this d0 because this is the distance where they are initially, is then equal to, we're going to import the math module so we can take a square root. So let's go up here and import the math library. And then it's the square root of dx times dx plus dy times dy. And down here, given this alternative starting point and its distance to our actual starting point, we can now work out whether or not a system of equations is actually chaotic. And this is what we'll now do down here, but we are only going to do that after a certain number of periods have passed. So we kind of want our system to, well, go through these 10,000 iterations, but the first couple hundred will only really be there to check whether we have this infinity or this fixed point attraction case. And only after that will we really go into, is it or is it not truly chaotic? So here we'll say if I is greater than 1000, only then are we going to go into this check for chaotic behavior. And what we'll do here is, well, we'll first compute where the alternative point now is. So we'll say compute next alternative point. And this is now xe new and ye new. And now I just got to add all of these e's into here. So that's going to take a couple of seconds, but not too long. E here, another here and there. And then lastly with the product of x and y. And there we go. So we now have our next alternative point. And given this alternative point, we can now compute the distance between the new points. So let me go up here and copy paste this down here. Gonna indent this properly. And now we'll say that we are computing the distance between xe new and xe, and the same thing with y. And then we compute the distance again, and now I'm just going to call it d. And given this distance, okay, there's actually a closing parenthesis missing here, but I got it up there. Good. And given this, we can now compute something that's called the Lyapunov exponent. So this is named after some mathematician who discovered this cool feature of what chaotic behavior looks like. And it's named after him. It's called the Lyapunov exponent. So this is really just an equation, and we will initialize it to 0. So up here, where is our converging Boolean? Let's copy paste this down here actually, right before we go into the iterative loop. And here we'll now also specify a variable called Lyapunov, and I'm going to set that to 0. So here, initialize convergence Boolean and Lyapunov exponent. So this is 0. And now once we've gone through this burn-in period, so to speak, and we're now in this next part of the process here, so after the first 1,000 iterations, we can now compute this number. And this number starts at 0, obviously, and then with every additional iteration after the first 1,000, we'll now add to that number. And what are we going to add? We're going to add the logarithm of the absolute value, that is just the difference between the relationship of our current distance and our initial distance. And then what's cool about the Lyapunov exponent, that in the very end, if that number is greater or equal to 10, then we'll know that we will have found chaotic behavior. So if we are not converging and the Lyapunov exponent is greater or equal to 10, then we know that we have found chaotic behavior. So check if chaotic behavior has been found. And okay, here it kind of says check for chaotic behavior. So here we'll just say if chaotic behavior has been found, then we'll set found is equal to true. Okay? And there's one more thing that we have to do, and this is we have to rescale our alternative point, because remember, they will go on to completely different trajectories. So this number, at some point, it's going to get really, really large. And if d grows to infinity, well, this was going to get pretty large, right? So it's no surprise that the Lyapunov exponent will be pretty big. So what we got to do is we have to go back and rescale our point. So let's go back here and copy paste our alternative point down here. And I'm going to now call this rescale the alternative point. And it's now going to be equal to x new and y new, but now not some random noise, not some random shock here, but we want this to be in proportion to how these two things have already evolved. So what we'll do is we say dx divided by d and dy divided by d, and then this has to be pre-multiplied or just multiplied with our initial distance. And this will make sure that this point is now also back sort of near towards where we are right now, and then we can run this check over and over again. So you're noticing that I'm not really going into the maths here. If you want to, you can read up in this book by Julian Sprott, which I'm going to link to in the description to this video. But we are more interested in the coding part here. So let's see if I have coded any additional mistakes here, or whether this is now going to be something worth looking at. Well, let's just give it a go, huh? Let's run this, and boom, we get something, but I'm going to run this again because it should produce cooler images than this. But I think this is working now. So you can really see how with every time that we run this, we now get a more interesting pattern. So close this, run this again, and here we go. So we now produce chaotic behavior, but not all the time. So here we get one of these images, which is not interesting, and this is probably because there's still something missing here. Yeah. And the answer is actually not too difficult. Right down here where it says xe new and ye new, we have to make this x new and y new. So this is all that we got to do, I think. And now let's run this again. And there we go. We get a pretty picture. Let's run this again. This kind of looked like a tornado. And here, look at this one. And now let's run this again. And there we go. So every time that we now run this, we will get, as a result, a cool, strange attractor. So this one, I'm sorry, this is now a bad example. I don't think it looks all too interesting, but I think this one here is. Now, I personally like those which have like a really a great distribution of points across the canvas. Oh, look at this one here. This is like a bunch of separate parts, and the points then jump into this other section here, and then stay within that vicinity for a while, and then jump back out of this again. And this is also really, really cool to look at. So we can now really generate a whole lot of them. And you know what I'm going to do? let's automate this so I don't have to rerun the script every single time. Let's just say that we want to find some kind of number, say 10 of these. And now we'll set found equal to 0. And then we'll say while found is less than n, then we'll have this running. And down here, it's now not true, but plus equal 1. So every time that we have found one, we'll increase the counter. So let's save this. And what are we going to do? While found is less than n. So if we find one, then we'll plot this. So I think this should work now. So let's run this. And boom, first image. I can now close this. And another one pops up. And now we have just really automated this process and we're getting every new images here. How cool is that? And okay, now I'm going to click through all 10 of these. I mean, if we wanted to, we could also say something like have a little print statement down here, which says found another strange attractor with L is equal to, that's the Lyapunov exponent string L, string Lyapunov. And then maybe plus, well, just another exclamation mark. And let's see if that works. We run this. And now I can close out of this, and you can see that it's now printing out all of the results down here. Anyway, oh, look at this one. This is also a really nice example here. What I now would like to do is I would like to remove the axes because we don't really need them. We're just interested in the picture. It doesn't really matter to us that we are on a scale from say 0 to 0.7 up here. That's like, has like no value to us, right? So let's go out of this. And what we'll do, I'm not going to set n to 1 because, you know, it just takes a while to close all of these images. And what we'll now do down here, we'll now play around with the plot. So here, update counter and have a little print message. And now we'll have our plot design, and I'm going to say pyplot.clearFigure. So if we have produced a plot, we don't want other plots to stack on top of that. That will be important when we are generating all these plots in sequence without me closing the windows in between. So you'll see the importance of this in a minute. And now we'll, okay, this is clear figure, and now we'll play around with the plot design, where we'll now say pyplot.style.use, and then we'll use, I think it's called like something like dark_background or something. And then we'll say pyplot.axis is off. So let's run this. This did not work as I intended it to work. So this is still a white background. The only thing that has changed is the fact that we now have a green color here. So the problem is that clear figure, we don't need this right now. We'll need this when we'll export these images. So let's save this without clear figure. We'll run this. And now you can see that we have a black background and we have green dots. Now we can change this to any color we want. So we could just go here, introduce C is equal to white. Let's run this. So we've just turned that into white. There you go. So let's export these. How can we save these? Well, we can now say, well, here, create the plot. And now down here, instead of showing the plot, I'm now going to save the figure. And now I'm going to need this. Because if I was just to save it without having the window appear and then have another one created, they would be created on top. And this just clears out the figure here. Alrighty, how can we save this? Well, we can just say pyplot.savefig, and now we have to specify a place and a name of the file. And I think it's good to save this in a separate folder because we're going to create a lot of them. So I'm going to go into my main directory and create a new folder, which I'm just going to call search. I also called my Python script search, but this is now the folder in which we'll store all of this information, all of these images. Now, if you're not working in an editor like Atom, where you can see like your project over here, just go into your Explorer window, your file window, and create this folder in the same directory as where your Python script is located. So you'll have one parent folder in which you'll have your script, and then you'll have, so this is the parent folder, and then you have this little subfolder here where you can store these images. Now, you can just call it whatever you want, the images, but I figured it's kind of cool to give every image a unique name, a unique identifier, so to speak, which means that if we're generating a lot of them at different points in time, so I might be running this today, and then I can run this tomorrow. I don't want the images of today or like of tomorrow to have the same name as the names that I've used today, because then I lose the earlier images because they'll just be, overwritten. And to prevent this, I'm now going to import a module called time, and from this I'm going to import something which is also called time. So from time, I'm going to import the time function, and this will now allow me to just timestamp these images. So I'll just give them a name, which is the string of the current time of my computer. And this will then mean that every image, regardless of when it is created, will have a unique name. And then what we must do is we must go into our search folder. So I'm going to use this. I'm going to add to it the time. And then lastly, we must add the file extension, which is a PNG file. And now we must also specify a resolution, which I'm going to set to 200. And well, let's just give it a go and see if we can use this to create 3 images. I'm going to save this and now run this. So it's now printing out these statements here. And in my search folder, I now have an image. And I have another one right here and a third one right there. And I think this is now so cool because now I can use this little script here and just say create 10 of these, create 100 of these, and in my folder I will then have all of these images to look at. And if I now zoom in on these images, so let's blow this up, you can now see that these points, they are sort of blurry. That's because we have used a low DPI value. And you can also see that it's not exactly like a single pixel. It's really just one pixel with a little circle around it. And to prevent this sort of thing, I'm now going to go into, where is it? The plotting part. And here we'll now specify that the line width is equal to 0. So this is kind of weird in PyPlot. Why, when you're using a scatter plot that only includes points, why do you have a line width argument? But that's just the way it is. So let's run this again. You'll now see that it's now going to create an additional 3. So let's open up one of the old strange attractors. And we'll zoom in here because I want you to be able to see the difference. So here's the old image. And now let's open up one of the new ones. Okay, I guess this is the only one that's really interesting here. And now I'm going to zoom in. And you can now see that here we have colored, in a way, individual pixels, whereas here it's kind of like blurred little circles, okay? And this will be even more, I mean, the difference will be starker if we increase the DPI. So you can really see that this is an individual little square, 1 pixel on the screen, and here it's kind of like a blurry circle. So let's exit out of both of these and wrap all of our code into a nice little function, which I'm just gonna call search. So here, let's just say def search attractors, and the user then must specify some n. Let's default this to 5 and go down here, indent all of our code, indent this, and now we can just say search attractors, and we'll specify how many. Let's search for 1. I'm gonna run this, and there we go. So found another strange attractor. I can open this up, and there we go. What a cool image, right? And remember, these images are kind of unique, and it's very unlikely that somebody has seen exactly this strange attractor. Now, some of them are very similar, but they are all unique, and this is what makes this so interesting to me, actually. Anyway, let's say we have created, I don't know, 20. So I'm going to run this now. So it's not going to print out all of these, found another strange attractor, and so on and so forth. We have all of these images. And now it's time to curate them. So we'll go here, we'll open them up, and we'll say, okay, this one is okay. This one is really boring. This one's not too interesting either. This one's kind of interesting. It kind of looks like the Tinkerbell map. Now, if you have not heard about that, check it out. Go on Wikipedia, open up the Tinkerbell attractor, and you will see an image which kind of looks like this, but this one has like 2 of these Tinkerbell attractors together. So that might be something that you would like to recreate, but the problem is that without the exact parameter vector that was used to create this particular strange attractor, and without the initial conditions, without the initial point, it's going to be really hard to recreate this image. Now, what can we do to fix this? Because right now, this is just a PNG file on our computer, but let's say we wanted to run this in greater resolution or with a different color, then you couldn't do that. And unfortunately, this information, it's kind of lost. We cannot recreate it. So let's make sure that this does not happen in the future. And a pretty simple fix to this, I'm now actually going to delete all of these because I don't want my computer to have too much unnecessary files on there. What we can do is, after we have saved the figures, we can save the parameters. Okay, so what we'll do is I'm going to define these parameters as a tuple. So this is from our X list, the first value, and from our Y list, the very first value, Y list 0, and then all of the parameter vector A. And now we got to save this to a file, and there are different options available here, but I'm going to go for a text file. So we can create this text file using, what am I doing? The command open. And then we have to specify the folder. So I'm going to use the same thing here. So let's take all of this, and you know what? Let's create a little variable here, which I'm going to call name. And then we can use this exact name down here once more. So let's copy paste this here. But instead of a PNG file, this is now a text file. And then we just have to specify, I think this has to do with how the lines are written to the file. So W+, don't bother with it too much. And then we'll just say file.write a new line with our parameters, which are now a string. So we have to write them as a string. So let's see if that works. Now I'm just going to create 3 strange attractors. I'm going to run this. There you go. And you can now see that we have the images as before. So one image, another one, and this one right here. And now we also have text files. And these text files, if I open them up here, you can see that it's just one line and it's a tuple. It starts with a parentheses here. And then we have the starting conditions, the X and Y, and then comes a list with, well, that is our coefficient vector for the quadratic map. And now we could close all of these. We could actually even delete those files. Not the text files, just the images. That's important. So I'm going to move these to my trash folder. And now let's create a new script, which I'm now going to call, I'm just going to call it draw. And here we can now copy paste almost the entire script actually. And now we can remove some of the parts. So I don't think we need the math module anymore. We don't need the random module. We are going to need this and maybe time also because we want to save stuff. Anyway, let's call this draw. And now we don't need the end anymore because we are now drawing a specific strange attractor. So here I'm now going to specify some X, some Y, or we can just say throw in the parameters. So because we can load them from our text files and then just throw them into that function. Then we don't need the found part anymore. We don't need the while loop because we are not searching until we have found a certain number. We know that this is going to work. So we don't have to search anymore, which means we don't need a random starting point. We don't need the alternative point. Distance, X and Y are now all defined. So unpack the parameters. X, Y, and A are equal to the tuple called parameters. Now comes all of this part. We don't need these booleans. We don't have to run any checks anymore because we know that it's going to work. We don't need the, we need the next point. But all of this, I think, is now, we don't need this anymore. And yeah, now here we don't have to make this an if statement. Don't need this anymore. And now it's really just about the plotting, right? So save the figure, but we don't have to save the parameters a second time. We already did that. And the only thing that I'm now going to do, I'm now going to have another folder where we have our curated results, so to speak. So let's go here and create another folder. Come on. New folder, which I'm going to call our gallery. And we'll now be saving to our gallery folder with a higher resolution. So let's bring this up to 1000. And then we'll go here. We'll use our draw function down here to draw a bunch of parameters. And these parameters, well, we can just copy paste them over from the text file. So parameters is equal to, then here, this is where we can now copy paste. Let's go back to search and let's see if we can find a couple of pretty looking strange attractors. So let's run this once more and let's have a look. So this is, I think, kind of interesting. And this one really is. And what about this one? Okay, let's go with this one here. So let's say I really like this image and I said to myself, I want to recreate this in higher resolution and I want to be able to print this on a large sheet of paper and hanging up in my living room or whatever. We can now go here and open up that text file associated with this image. So we can go here, we can now copy paste this, go into our draw script, insert this right here, go into the next line where it says now draw parameters, and if we coded everything correctly, we should now be able to run this. I'm going to save this and run it. So it's not going to take a while. Oh god, no. I just made a horrible mistake here. Let's go here and the gallery folder is exploding. Let's clear out all of this. Some of you might have noticed this while I was coding this. I was drawing within the iterative loop here, right? And we don't want that to happen. So this is only after we are done with the drawing. So this needs to go out of here. And let's give this a second go, a second run. And now the gallery has one image in there, which was created after 2 seconds, which is a lot more reasonable. And let's open this up. And there we go. We now have the image. And let's close this and this as well. And well, I think it was this image here. So this was the low res version, and here this is now the high res version. Now it's kind of hard to tell the difference unless you zoom in a little. So if you were to print this out on a larger scale, you'll immediately spot the difference. So let's go here and go down a little. And yeah, there you go. So you can now see how we can really zoom in a lot further without the image being too blurry. Because if I zoom in like this, you can really see how the image is just not as sharp, right? So yeah, anyway, this is how we have recreated this strange attractor. Let's go back out of here. And yeah, you can now play around with this, make this whatever you want it to be. So we could say instead of having a dark background, we could go for a white background. We could experiment with different colors. We could change the DPI, and now it's really up to you to discover as many strange attractors as you want. Use your search script, run it, and specify whatever many parameters you would like to look for. Maybe you would like to go for 20 new strange attractors. So you can now run this, and the computer will produce ever more strange attractors all over here. You can then look at them on your computer. You can find the most attractive ones of them. The most attractive strange attractor, how cool is that? You can find the ones that you really like, and then you can open up the text files, copy the parameter string, paste it into your draw script over here, and then execute that, and boom, you will have the image that you would like to have. You can play around with it and yeah, create some cool images. By now, I hope that a lot of you feel the strong urge to close this video and start running your own code to find your own strange attractors. If so, I think this video has served its purpose. And if you think so too, leave a like, write a nice little comment, subscribe if you haven't already done so, and most importantly, tell some of your friends about Coding Cassowary. See you in another coding project.